In this chapter, we will be studying systems of linear equations. In this particular lesson, we will be looking at solving systems graphically.
All right, now we're going to start a chapter that maybe at the front, it might not seem like it, but this is a chapter that usually people end up doing fairly well on because the math ends up making a lot of sense here. And you'll see that hopefully as we move through this that the pieces that we look at and how things all work together, this is a really nice chapter. Okay, so we're looking at systems of equations, and to start off with, we're going to start by solving systems of equations graphically. Okay, now a system of equations consists of two or more equations with two or more variables, okay, that are considered together. Now, I want you to think of it like this. If I gave you what is this? Let's say 3x plus 6 equals 0. Okay? I've got one equation, one unknown. But there's enough information here for me to solve this. I would move the 6 over. I would get 3x is equal to negative 6. Divide by 3 and I'll get that x is equal to negative 2. Okay? And so I have now figured out the value of that variable that makes this a true statement. If you plug negative 2 in there, 3 times negative 2 is negative 6, plus 6 is 0. So the left side does equal the right side. Now, if, however, I had, let's say, 3x plus 6y equal to 0, well, now I've got two variables in here, but I've only got one equation. There isn't actually enough information here for me to determine what x and y are. The best that I can do is determine a relationship between them by solving for one of the variables, and usually we would solve for y. And so what we would get here is that y is going to equal, you would bring that over and you get negative 1/2 x. But that's about the best you can do here. If, however, and you'll see that down here, if, however, you've got two equations with two variables, that is enough information for me to determine a specific value for x and a specific value for y. That makes both of these equations true simultaneously. So there is a point out there, for example, that if I plug in that x into here and the y into here, and I plug the same value of x and y into here and here, I will get 7 in the first equation and 1 in the second equation. Okay? So that's what we call a system of equations. Now, if you've got three unknowns, if you have x, y, z, then you can probably guess at this point that you would need three equations to solve for that. Now, a linear system of equations is one where each one of these equations is just a straight line if you were to graph it. And we've already had a fair bit of experience with what these look like. And notice right here that these are both in standard form. In this particular chapter, standard form is going to be one of the more useful forms of the equation of a line. Now, that hasn't really been the case for the last chapter or two here, but it will be here. Okay, so let's talk about it. When you've got a system of equations, you've got two different equations here that you've graphed. Where do you think the solution would be? I mean, now we've already kind of, you can see from this diagram right here, there's a bit of a push towards that point of intersection right there, because that is in fact the point that's the solution to this system of equations here. It's the point that lies on both lines. Okay? Now, this particular solution is the solution to the system here. Now, I'm going to make sure I look at it right here. This is the solution actually to the system x plus y equals 7, negative 2x plus y equals 1. It's not exactly the system that was up here. There should have been a negative right here. In fact, I probably should write that there. The system, the solution 2, 5, or the point 2, 5 is the solution, because if you plug that in, 2, 5, 2 plus 5, you get 7. Negative 2 times 2 is negative 4, plus 5 is 1. So you can see by substituting in that point, okay, this point 2 comma 5 into this equation and into this equation, okay, plug it into there, it makes true statements out of both of those when we evaluate. That's what it means to be a solution to a system of equations. Okay, it's the point of intersection. In fact, that's probably the best way we can write this. The solution of a linear system, and it doesn't necessarily have to be a linear system, but that's what we're talking about right now. The solution of a linear system is the point okay, the point of intersection. Okay? Now, I say it like that because I need you to answer as a point. Okay? The solution to this system is 2 comma 5. Now, this is what I've seen people do in the past. I've seen people say, oh, x is equal to 2, y is equal to 5. And tell me that that's the solution to the system. Actually, that's not the solution to the system. This is not the solution to the system. And the reason I say that is because what is x equal to 2? Well, x equal to 2 is a vertical line. What is y equals 5? Well, y equals 5 is a horizontal line. Now, those two lines happen to intersect at that same point that I'm interested in. But when I ask you for the solution to a system of equations and you simply state another system of equations, you haven't answered the question. Likewise, if you were to write this, 2 comma 5, that's not the solution to the system either. And I have all sorts of students that have done this in the past, and it's something that we really got to clarify here. There is a beauty to the way math is communicated, okay? The symbols mean things, and if you have an absence of a symbol, that typically means something too. If you don't put the parentheses here, this is just a list of numbers. This is just the numbers 2 and 5, okay? But that's not the solution to the system. The solution to the system is the point 2, 5. As soon as you put the parentheses here, I know this is the value of the independent variable. I know this is the value of the dependent variable. All of a sudden, the position here has meaning. If you don't, okay, this is not the solution, this is not the solution, that's the solution. You need to write it as a point. In fact, in this particular chapter, the only time that it is acceptable to write your answer not as an ordered pair is with the word problems. And I think that'll make sense when you get there. It makes more sense to simply answer the word problem the way it's been asked. Okay, and so in whichever way they ask the question, to answer it in the way they ask it. All right, now let's have a quick look at just a couple of examples here. Find the solution to each of the following. Okay, well, here's my system of equations here. Essentially, they're just pushing you without even knowing what the equations are, just looking at it graphically. What I'm looking for here are the coordinates of that point of intersection. And what I see here is I come back 1, 2, 3. It looks like -3, and then 1, 2, 3, 4. So the solution is the point -3, 4. Okay. Over here, when it's a table of values, I've given the equations here, but what we're looking at here are we're looking at the points. But what I'm looking at is the place here, the specific point where the y coordinates are the same, and we can see that that's true right here at -3, 12. And so that is the solution to the system of equations implied here. Now, recall that when you're going to graph a line, you can use any of the previous methods that you've used. You can use the x and the y intercepts if it's written in standard form, and it will often be written in standard form. Okay, and I say that, and I say that with some conviction here, because in a couple of lessons we're going to look at a method of solving called elimination, and almost all the time we will have the equations in the standard form when we apply that particular method. Or make sure that you're using slope y-intercept form, right? So you're going to take that equation, isolate the y, and as soon as you've isolated the y and simplified, it will automatically be in slope-intercept form. I know that was a little bit confusing for some people in a previous chapter here, but just believe me, if you take standard form, bring the ax over, divide by b, as soon as you've divided by b and simplified what you get on the right-hand side of that equation, what you're left with will be in slope-intercept form, and you should be able to identify the two pieces you need to sketch it. All right, let's just try our hand at solving some systems of equations. So here we go. So here's our system over in this right-hand corner. X minus y is equal to 7, x plus 5y equals -5. Okay, well, I tell you what, one of the things that you're going to see, because when you go into university, there's a math course that you'll take, and a lot of people take it. It's called linear algebra. You're going to end up seeing systems of equations again. And one of the things that they do is they'll label these things with numbers in circles here, so you recognize that those are the labels. So I tell you what, for this first equation here, for number 1, I'm going to just isolate the y, okay? So x minus y equals 7. I'll bring the x over, so negative y is equal to negative x plus 7. Remember that when I move the y over, it changes signs. But the y stayed negative because it didn't move. And I'll divide by the negative, and I'll get positive x minus 7. Y equals positive x minus 7. So what does that look like? Well, that's a line with a y-intercept of negative 7, so down here, and a slope of positive 1. So it's going to go up 1 over 1, up 1 over 1. And I'm just going to identify all those points, and then we'll draw a line through. And then I'll just indicate that we've gone off the edge there. Okay, now 2. I'll do this a different way here. Maybe what I'll do is I'll find the intercepts. So the first thing I'll do is I'll find the x-intercept, and I'll do that by simply making the y-coordinate equal to 0. And now if I do that, that term disappears, and I'm going to get that my x-intercept here is negative 5. Okay. The y-intercept, if I make the x-coordinate equal to 0, and then divide both sides by 5 to isolate the y, well, negative 5 divided by 5 is going to be negative 1. So the y-intercept will be negative 1. And so what that will look like, okay, I'll have a slope of x-intercept of negative 5, so it's right here. And then a y-intercept here of negative 1. Now, what I've got here in terms of my slope, I go down, down 1 over 1, 2, 3, 4, 5. So down 1 over 1, 2, 3, 4, 5. Oh, look at that. That goes right on top of that point that I've already highlighted. That's the point of intersection. So I just have to read off the coordinates now. So that's going to be 1, 2, 3, 4, 5, 1, 2. So 5, negative 2. 5, negative 2 is the solution. Now, I can do this on my calculator. Okay, and I'm going to show you how you do this here. The first thing you got to do, though, is you got to isolate the y in both cases. You basically have to do what I did for equation 1 here. Now, I've already done this and entered this into the calculator. If you go to my y equals, you'll see that I have the x minus 7. And if you solve for y, in this case right here, you bring the x over, so it's going to be negative x minus 5. And then when you divide by 5, you'll get negative 1/5 x minus 1. And now I'll just graph this with my regular old zoom settings. Now there are a couple of ways that I can figure out that point of intersection. If the point of intersection is on the natural lattice of the coordinate plane, in other words, if it's got nice integer coordinates, really all I should have to do here is press second graph to access the table. Whoops, sorry, and yep, let me just fix that. I know, I was doing some work the other day and showing someone how you can use the calculator to solve periodic functions. Anyway, so I'm going to change the way my table goes up. Yours should probably be okay. And if I come down, I'm just looking for where the y coordinates are the same. And if you come down here, there it is. When x is equal to 5, in both cases y is equal to negative 2. There's my point there, 5, negative 2. Another way of doing this is to press second trace to get into the calculation menu. And then I'm going to come down and use option 5, intersect. Press enter. Now what the calculator does here, it then puts you on the graph here, and it's going to pick one of the curves. So it's going to be the first one that you entered in. And it's basically just going to sit there and say, hey, is this the first curve? And the reason it asks that is because you could technically have 10 different curves drawn there. It just needs to know which one is the first one. So just press enter, and notice that it jumps to the second curve. And it asks, is this the second curve? Yes. Now it asks for a guess. Now the purpose of the guess is to help speed up the calculator. So what we're going to do here is we're just going to move that cursor a little bit closer to that point of intersection. Press enter, and then it immediately jumps to that point of intersection. 5, negative 2. So there we go. 3 different ways that we can find that point of intersection. Now you're going to see, over the next couple questions, I'm going to keep coming back to the calculator because I want you to be able to do both by hand and with the technology that you've got available. Okay, now this question is very similar to the one that we just did. Graph the following system of equations and determine the solutions. All right. So there's equation 1, there's equation 2. Now notice both of these are in slope-intercept form, which makes it a fairly convenient thing to graph here. Notice that the y-intercept is negative 1 for the first graph, and it's got a slope of positive 1, meaning I would go from here up 1 over 1, up 1 over 1, up 1 over 1, and there we go. Now, the reason I am not just plotting 2 points and then drawing my line there, the reason why I'm filling in all these dots here is because in most cases in this particular chapter, because we're not trying to make this super difficult, particularly to start off with, your point of intersection is typically going to fall on one of these lattice points. And so I'm just going to identify all of them that are on that line that I can see right here. And odds are pretty good that when I graph the other line, I'm going to fall on one of those points. Let's just have a look. The y-intercept is negative 3. It's going to be down here. And it's got a slope of 3 over 2. So from here I go up 3. 1, 2, 3 over 2. 1, 2. Up 3. 1, 2, 3 over 2. And there it is. There's the point that we overlap on. But I want to continue to draw this, so I would go up 3 from here. 1, 2, 3 over 2. I'm right there. Now, I would also go backwards here because I want to fill this in as much as I can. So I would go down 3, 1, 2, 3, backwards 2. And there we go. And I will draw my line. Okay, there's my second line. So here was equation 1, here was equation 2. And the point of intersection was the point 4, comma 3. And then again, we can verify this using the calculator. And again, I've already entered these in. So y equals x minus 1, y equals 3 over 2x minus 3. Once again, I can go to my table of values just by pressing second graph. And I come down here, and there it is. When x is equal to 4, in both cases, the y-coordinate is 3. Or, on my graph, I can press second trace, go down to intersect, and again, it puts me on that first graph. Yes, that is one of the lines I'm interested in. Press enter. It jumps to the second one. Yes, that's one of the lines I'm interested in. Press enter. Now, it's asking for a guess. You might want to just move the cursor close. You don't have to put it right on top of. I know some people feel better doing that, but you don't have to. You just press enter, and then really quickly you get the point 4, comma 3, which is what we found previously. Okay, here's another one. So again, we'll mark this as equation 1, equation 2. Now, to plot equation 1 here, I can do this a couple different ways. I mean, I used the slope-intercept in both form in both cases in the previous question. I tell you what, let's look for x and y intercepts. So let's look for the x-intercept first. Okay, when I do that, I make the y-coordinate equal to 0, and that tells me immediately that my x-intercept is 3. And if I want my y-intercept, what I would do in that first equation is make x equal to 0, which makes it go away. And then I've got negative 2y equals 3. Well, then just divide by negative 2. And I will get negative 3 over 2. So I can plot that. There's 3 as my x-intercept. Negative 3 over 2 is negative 1.5. That's going to go right there. Okay? Now that is kind of an awkward little point there. But notice what's going on here. I go up 1.5 over 3. Up 1.5 over 3. Down 1.5, backwards 3. Down 1.5, backwards 3. So that does give me enough that I can plot the points. Now let's take a look at equation 2. I could do the same thing there. Now, you're going to find right away that this isn't quite enough. But in this second equation here, if I look for the x-intercept, if I make y equal to 0, x equals 0. And then you're probably seeing it right now. If you make x equal to 0, well, y equals 0. Now, unfortunately, that's the same point. That's the origin. So that actually isn't all that particularly helpful to me. I actually do need to put this into slope-intercept form because I need more than just that one point. But that's okay. As soon as I do this, as soon as I move that x over, I can see that the slope is negative 1. So from here, I would go down 1 over 1. Okay? Down 1 over 1. Down 1 over 1. Down 1 over 1. Down 1 over 1. And I can go backwards and I pick these points right here. Now, something happened there that was not exactly the way I described it happening before. Where these guys overlap was not a point that I actually plotted when I drew that first line. So, okay, I'm seeing a point of intersection. It looks a lot like the point 1 comma negative 1. Okay, it looks an awful lot. So here's a great example of a time where what I should really do right now is verify this. Now, I didn't do that in the previous two questions because really the overlap was quite obvious. Okay, and we're just kind of building up on these ideas here. So right now, again, because that particular point was very clear on one line but not so clear on the other, let's just verify that that is in fact the solution. And this is how we do it. We're going to take equation 1 and I'm going to plug in the coordinates that I got here into my equation. So x is 1, y is negative 1. So that's going to be 1 minus 2 times negative 1 equals 3. Is that true? What is 1? Negative 2 times negative 1 is positive 2. Is that true? Yes, that is true. So I know that it satisfies that first line. And does it satisfy the next line? If I plug in the point 1 and negative 1, does that equal 0? Yes, it does. And so, yes, I've been able to verify that that is, in fact, the solution that I was looking for. That's an important thing to know how to do here, because often when you graph these things, when you graph them by hand, let's say, it's very hard to have faith in your work, I suppose. You want to, but it's sometimes hard to believe that that's actually what the correct answer is. Now, once again, though, you could enter that into the calculator. Okay, press graph. There's what my graph looks like. Again, I could go to my table of values and look right away when x is equal to 1, y is equal to negative 1 in both cases. Or I could go back, choose the intersect feature. Now, they're all kind of close in there, but you can see that the cursor's on the first curve. Press enter. Is that the second curve? Yes, press enter. And then just press enter to get past the guess. And there it is right there, once again verified. The point of intersection is the point 1 comma negative 1. Okay, so we've done some examples where you were solving. And you've kind of seen a couple different approaches to each one of those, which is good. Now we're just going to take a quick look at a question that should be a fair bit easier to attack here. Just verify that the ordered pair 3, 2 satisfies this particular system, okay? So here's equation 1, here's equation 2. Now to show that to verify that it satisfies that system or that it is a solution, we're simply going to plug this point in. So for equation 1, we will plug it in. So it's going to be 4 times x, well the x coordinate here is 3. If this is a solution, the x coordinate's 3, minus the y coordinate 2. Does that equal 10? I don't know, but 12 minus 2, does that equal 10? Well, yes it does, so good. So we know that that particular point does satisfy the first equation because it gives us a true statement. 12 minus 2 is in fact equal to 10. Now let's see if it satisfies the second equation. So the coefficient of x is negative 2, so it'll be negative 2 times 3 plus 2 equals negative 4. Okay, well, is that true? This is negative 6 plus 2. Is that negative 4? Yes, it is. So yeah, right there we've been able to verify that yes, it is true that the point 3, 2 is a solution to this particular system. You are going to be expected to be able to recognize that on the exam. Okay, this next question here, this is a popular one to ask, and you will see this one come up again when you're in Math 30, for example. A question very, very similar to this in style, and all they do is they make the question just a tad more challenging when you get to Math 30-1. It says, for what values of m and n, so look in the equation where they show up, is the point 25 the solution? So we're going to assume that that point 25 is in fact a solution to this system, meaning, okay, that when I plug this in for x and y, the equation is satisfied. So for equation 1, that means m times 2 plus 5 is equal to 19. Well, now notice I've got an equation here, a single equation with a single unknown in it. So I can solve for that. This is m times 2 is equal to, well, subtract 5 from both sides, you can get 14. And when you divide by 2, we get that m is equal to 7. So I know what m is. Now I'll do the exact same thing with equation 2. Okay, that's going to be n times 2 minus 2 times 5 is equal to negative 6. Okay, and now I've got a single equation with only a single unknown in it. So n times 2, now negative 2 times 5 is going to be negative 10, and that's equal to negative 6. So n times 2, I'm gonna add 10 to both sides. So negative 6 plus 10 will be 4. And when I divide by that 2 to get n all by itself, I'll get that n is equal to 2. And so the values that I'm looking for m and n are 7 and 2. Now, notice I don't need to write this as a point, okay? Because that was the point of intersection here. I'm just evaluating for the values of those two variables, basically parameters in the equations. Okay, now we're going to take a look at a couple of word problems. Now, the word problems here, we're really kind of leading you through this. In fact, you can see right here, we've given you the equations. So it's not quite the same sort of thing here. In a little while here, this is going to be what the goal is. You're going to work with word problems where you're going to have to determine what the system of equation is. Okay, so let's take a quick look though. Jerome purchased a small and large multi-packs of yogurt. Okay, each small multi-pack contained 4 yogurt cups and each large one contains 12 yogurt cups. Jerome purchased 9 multi-packs for a total of 60 yogurt cups. If S is the number of small multi-packs and L is the number of large multi-packs purchased, a linear system that models the situation is. Okay, so right here. So think about what's going on here. So if you've got S plus L, the number of small cup multi-packs, the number of large multi-packs, we know that that's equal to 9 because that's what we were told. He purchased 9 multi-packs. And he got a total of 60 yogurt. Now, how did he get that? Well, for every small multi-pack, he's got 4 yogurt, and for every large multi-pack, he's bringing in 12 yogurt. So S times 4 plus L times 12, that has got to equal 60. Okay, now we're going to graph this. Now, you have to make a decision because we're not using X and Y here. You kind of have to make a decision. Which of those variables is the independent variable and which one is the dependent? Now, on the face of it, that question really doesn't make a whole lot of sense because the number of small packs of yogurt, the number of large packs of yogurt, they are not dependent on each other at all. But if we're going to graph it, you kind of just need to make a choice here. So in this particular case here, you'll notice that S was chosen to be the independent variable and L was chosen to be the dependent variable. So in other words, to graph this thing, I'm going to solve for L. So here's equation 1, here's equation 2. So now equation 1, when I solve for L, L is going to equal negative S plus 9. And in equation 2, when I solve for L, well, the first thing I would do would be to bring the 4S over. So 12L is equal to negative 4S plus 60. And when I divide, L is going to equal to negative 1/3 S plus 5. Okay? And there you go. Those are our two equations. Now let's just plot them. So first of all, look at this first one. L equals negative S plus 9. So my y-intercept here is going to be 9. And I've got a slope of negative 1. So down 1 over 1, down 1 over 1. And I can see the pattern that's developing there quite clearly. I'll draw that down. Now, I mean, I could continue to extend the line over, but the truth is it doesn't make any sense to talk about negative multi-packs of either one of these things. Additionally, it's just something to be aware of. I know that the data here is discrete. That I really shouldn't have plotted that line or I shouldn't have connected the dots on that line. I know that. We go back to a couple of chapters here. We talked at length about that. I know that. But for right now, we're just using this word problem to help illustrate the idea of solving a system of equations. So please forgive me for doing that. There is kind of a larger goal here than just figuring out how many yogurt cups this guy, or yogurt packs this guy bought. In the next case here, the y-intercept was positive 5, and the slope was negative 1/3, meaning we drop down 1, go over 3, drop down 1, go over 3, and there it is. There's the point that is the overlap between the two. But I'm going to keep going, drop down 1 over 3. And so this one goes like that. Now, my solution is going to be the point 12, 3, which means 12 small multi-packs were purchased and 3 large multi-packs were purchased here. Now, and again, bear in mind that in this particular case, it probably makes more sense to write the answer like this than it does like this. Simply because, and here's a great example of it, what order should those variables really have been in? I mean, does it matter whether the small one comes first and the large comes second? Not really. Okay, so the order there is maybe a little bit ambiguous at this point. It just clarifies it totally if I just state 12 small were purchased, 3 large were purchased. Okay. All right, here we go again. Just another word problem. Again, just another context to help, again, illustrate the idea of solving a system of equations and what it's important for. And again, I'll state this right up front this time here that, I mean, I realize the data that we're dealing with here is discrete, okay? So we're expecting a solution that's a nice, clean solution on a lattice point. But again, I'm going to draw these things, the lines in, just so that it's very clear and just to emphasize again what it is that we're doing when we solve a system of equations. So here we go. Annika purchased sleeves and boxes of golf balls. Each sleeve contained 3 golf balls and each box contained 12 golf balls. Annika purchased 7 packages for a total of 48 golf balls. So there's all the information together that we need basically up to that point. Okay? We know what's in each pack, what's in each sleeve, and then there's a relationship here kind of combining packages and sleeves together. Now, if S is the number of sleeves purchased and B is the number of boxes purchased, okay, and again, we're going to talk about independence and dependence here in a bit, and there really isn't any relationship between them, so you can kind of make your decision on that. We just want to know what the system is going to be to solve that. And again, in a couple of lessons, again, this is going to be the thing that you're going to have to work on. So anyway, here you go. So the number of sleeves plus the number of boxes we know, as we were told, is 7. And then when you consider the total number of golf balls that have been purchased here, well, there's going to be 3 in every sleeve and 12 in every box for a total of 48. Now, to plot this and to figure out how many sleeves and how many boxes were actually purchased, we need to make a choice as to which variable is dependent, which one's independent. And you can see from the graph here, in this particular case, we're kind of pushing you to make the number of sleeves the independent variable, the number of boxes the dependent variable. And so that means equation 1 would look like this. I'll isolate B. B will equal negative S plus 7. Okay, and I can graph that. And then in equation 2, it takes a little bit more work. 12b will equal negative 3s plus 48, and then I'll divide by 12, and so b will equal negative 1/4 s plus 4. And now I've got my 2 equations, and I can plot them over here. So negative s plus 7 is going to have a y-intercept of 7, and then a slope of negative 1, meaning I'm going to go down 1 and over 1. And it's going to be all of those points. So I suspect one of those points there is going to be the solution. My second equation has a y-intercept of 4 and a slope of negative 1/4. So down 1 over 4. 1, 2, 3, 4. And there it is, right there. There's the point where they overlap. Now I'm going to keep doing this though. 1, 1, 2, 3, 4. Give myself a couple of points so I can draw the second line. But I can see right away my solution is going to be, oh, shoot. I did not read that carefully. Oh, this is a good learning moment. This is a wonderful learning moment here. If I was in class right now, I would be stopping and asking, does everybody see my mistake? Does everybody see my mistake? I flew through that, wasn't even giving it 2 thoughts here. Look at it. I hope you see my mistake. Okay, if not, then I'll have to explain this to you real quick. I did not look carefully when I jumped into the graph here. I did not look carefully at the scale. This is not going up by 1s. This is going up by 2s. Vertically, though, it is going up by 1. So now, when I plotted this, negative s plus 7, the y-intercept here was 7. I got that right. But down 1 over 1 puts me right here. Down 1 over 1 puts me there. 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 The line is actually a fair bit steeper than what I had drawn it. Okay? The next one here, y-intercept of 4. Now, when I go down 1 over 4, that's going to be down 1 over 4. 1, 2, 3, 4. And then down 1 over 4, down 1 over 4, down 1 over 4. And now I can connect those dots. Now, I'm still actually intersecting there, but this point is now back a little bit further from where it was. So now I'm seeing that the point here is the point 4, 3. Okay? Now, the number of sleeves purchased, well, S, again, that was we treated that as if it was the independent variable, so it's going to be 4, and the number of boxes purchased in this case was 3. And again, it makes more sense to answer it like this than it does to answer it as the point. I hope that makes sense. Please take some time to work through the assignment.